So the first speaker of this part of the event is Dr. Nikolaos Papahristou. He got his PhD at Department of Applied Informatics of University of Macedonia in Greece. And the reason we were very interested in inviting him to come to this conference was his work is intersection of backgammon, AI, and software engineering, all of them that we are interested in one place. So he was a great person to invite, and he was very kind to accept our invitation. He's going to talk about Palamedes, algorithms, and architecture of a superhuman AI for backgammon and its variants. Dr. Papahristou, please go ahead.
Thank you for the presentation and the introduction. Yes, I will talk about this research project that I started a few years ago called Palamedes, and how I created an expert AI for backgammon, and especially some variants that I was interested in. So when I started this project, I searched a lot about what was available for AI or for game-playing agents beside backgammon, but I couldn't find anything. So everything was only for the backgammon game. It was and only for matches, for matches for one variant only. We could not, the pre-existing literature could not handle some cases that were interested in Greece, where I come from, where we play backgammon games in a match, but not only in a match, there are a few, 3 different game times in the match. So I started this project with nothing available on these variants that on other variants that I was interested in. So also the search component of all agents that were available was not something that was separated. Most of the time this was integrated deeply in the engine. So the Palamedes research project tries to support a variety of backgammon variants, and especially the Greek variant called Tavli, and different game types, as I said, to investigate what the search aspect of the computation takes part in the whole infrastructure of playing the game, and also develop some special enhancements. And the ultimate goal is to achieve superhuman AI for every variant that we can support. So the outline of the talk will be in 4 parts. I will start with the evaluations and the learning, what is an evaluator and how can we learn, how can we train an evaluator to play backgammon and variants. And then I will talk about the search aspect and the specialized enhancement that I have made. And thirdly, I will talk about how to incorporate match algorithms in order to play efficient matches. And finally, I will talk about the system architecture of the agent and the whole project overall. Now, starting about the first part, which is the evaluators and the training of the evaluators. So when we want to train when we want to have an agent that can play a game, we usually want to have an evaluator of the state of the game. So there are 2 approaches. First, we can have an evaluator that takes the starting state. For example, we have the starting state of backgammon and the roll 3-1. And this evaluator on the left side can take the starting state and the move, and then it can predict a value for the state. And then we will do this for all the available moves and select the move with a higher value. And there is another approach where we can take the so-called after state value when we take the state that has been played after the move, and we pass only this to the evaluator, And then we have to select the move that results to the after stage with a higher value. In this project, we selected the second approach, taking the state value, the after state value. So there can be a lot of types of evaluators, and for this project we have maybe 4 or 5 types of evaluators. These are the most common ones. The basic evaluator is a neural network evaluator that takes the state, the after state, and computes the probabilities, the outcome probabilities, which is in our case these 3 outputs of the neural network, and then we can take these outputs and produce the state equity. There is another type of evaluator, for example, the Bear-Off evaluator, DB evaluator in the right side. We could pre-compute all the Bear-Off states and store it in a database, and then we won't have to do search or any kind of computation. We can just retrieve the value from the database. This is an example of another type of evaluator. So how we can train a Backgammon evaluator? Again, the most common approaches are these 2. First, we can do it with a supervised learning approach, where we could find some games played by humans and or computer generated, and then we could do supervised learning with those games. The strength of this approach is that it learns the human style of play and is computationally cheaper than the other approach. But there is some weaknesses that the model that is learned is capped by the skill set of the dataset. So it learns about the positions that are occurring in the dataset, and it cannot learn effectively other types of positions. So there is also the other approach that is used in the Palamedes project. It's the self-play reinforcement learning approach, where the agent generates games playing by itself. The targets for the learning are the estimation of the current evaluator, and this initially plays randomly, but gradually gains strength. The strength is that of this approach is that it can surpass the human knowledge because it isn't restricted by the human knowledge and the human games that are available. But the weaknesses is that this is mostly is very difficult to converge optimally because it can be stuck in local optimum. So a quick review of the basic algorithms that we use in the Palamedes project. It is the temporal difference learning algorithm. Most of you already maybe you know. This is TD lambda, a bootstrapping stochastic approximation algorithm, where we have the delta t is the temporal difference error, and the lambda parameter, where we can control how much the future affects the present during the updates that are doing to update the value of the states. So when we have lambda equals to 0, then only the next state changes the current state, and for the other part where lambda equals 1, then TD lambda resembles the model Cal sampling. So especially in this project, I use the forward view of TD lambda, which is shown in this equation. And there is an example how TD lambda with a value 0 or a value lambda value 1 or lambda value 0.2 affects the target of the state for the training. So, and also we use 3 output values for the neural network. So it's the win outcome, the win of a double game, and the probability of losing a double game, WT and LT. And here is an example of a simple algorithm like using self-play with TD0 that we use to train neural networks. After initialization of with the random weights, we started to play games using the neural network. And when we initially play a game, and then when we finish playing the game, we start the training. And then we update the weights incrementally. So this is that is all for the evaluation and learning. Let's go to the search and specialized enhancements. And with this approach, when we have a model, we train the model and we train the evaluator. This evaluator with this approach is very good. It can play good moves most of the time, but there are some times that the situation on the board is very complicated and the evaluator cannot find the best move. This is where search comes forward. We can traverse the game tree and to find maybe to get more information and find a better move. So the basic algorithm that we can use in a game where there are chance nodes, such as Backgammon, is the expect max algorithm. The pros of this algorithm that is accounts for all the uncertainty if we know the chance probabilities, of course, and maximizes the expected value, and is very good for a stochastic game like Backgammon. But there are also some disadvantages because it requires full knowledge of the chance probabilities. This is not a problem in Backgammon. We have the full knowledge of the chance probabilities, but it's very difficult to prune because it is very slow when we go deeper into the search tree. So there are some tricks that we use to prune the nodes. And one trick is an already known algorithm. It's the iterative deepening depth first algorithm. This combined with filtering. What do we do here? We repeatedly perform depth-limited searches, and when we go deeper to the tree, we don't go with all the moves, but we filter them according to the result that we got from the previous iteration. We have some predefined filters from the beginning that we will use when going down deeper into the tree. Another trick that is very useful is that we can expand only the best state on decision nodes. This massively prunes the tree. Of course, for this to work correctly, we have to have a good evaluator. But as I said, most of the time the evaluator selects a good move, so this is not a problem. And finally, there is a key value cache where we store dream values that for nodes that reappear in the search tree. So we see in this starting position, if we let the basic algorithm go down the search tree, expect max, we will soon reach in the fourth ply in 2 billion plus states. And we see now that with all these enhancements, this amount of states that we must examine in the fourth ply is only about 3 million orders of magnitude less states to evaluate and analyze. So another trick that we can use is we call it the pruning nets, because in the Backgammon, in some positions there are very many moves, and the evaluator can be very slow if we have to evaluate, for example, 2,000 moves. This is the extreme case. So what we can do is we can train another slower and faster, not so good, but faster evaluator, and we can just rank these states, all these states with a faster evaluator, and then select a small percentage of them to give them to the better evaluator and slower evaluator, and then we will select the move from the better evaluator, but we will have to. We had much less computation. So another trick that we have used in the Palamedes project is we have created batch versions of all the algorithms, because standard algorithms like expect math examine one state at a time, and this approach does not take advantage the parallelization of the model processors that we have available. So we have versions of nega expected match, which is the nega formulation of the expected match in the batch version, and the IDDF as a batch version. So now we go to the next part where we examine how we can make an agent play good in matches, well in matches. So first, to explain the situation, we have in Backgammon, we have the simple games, the single games, which we are called money games, where the goal of the player is to maximize his or her points from a single game. But typically, players do not play these games. They, especially in Greece, we play Backgammon in matches, where the goal of the player is not to accumulate, to get points. The goal of the player is to get points, but the ultimate goal is to win the match. So in typical Backgammon matches, the first player of the individual games is usually determined randomly. But in the table match, where we wanted to investigate, it is very popular in the match type in Greece, the winner of the game plays first the next game. And also I give you here a typical order of a table match. This is the three games that are played, Portos, Plakoto, and Fevga. These games are played consecutively, and then we cycle and play again these games. So we can have a table match for 5 to 7 points, or to 9 or to 11 points, and the winner of this match is the players and the agents need to know not only how to play all three games, but also how to take advantage of the match situation. So what was available before for the individual matches? For the individual matches, one way to play the correct move is to use a match equity table. A match equity table is just a matrix that shows the probability of winning the match from a given away score. So here, if the match score is 5-3 up to 7, the away score is 2-4. And if we go to the table, we will see that the 2 and 4 is in this situation, we have 68. The player that's played first, with one with the 5 points, has 68% of winning. And then we can take this value and plug it in this equation. And we will now take not the value from the position. We will also take the value from evaluator, but we will want all these to calculate the match winning chance, not the equity, but a value that estimates the probability of winning the match. This is called the match winning chance. And of course, if we do this for all the moves, the after states, and we select the state and the move with the best value. So what can we do for the table match? We can create also these mats, but now the situation is more tricky because we must examine what is the next match. We must first create mats for all three games. We have created these mats for Portes, for Plakoto, for Ferba, taking into account the order of the games played in the match. And then we will, when we want to compute the value for the match equity, we take the match score, the way score, the outcome estimation from the evaluator, but we also want to select the correct mat, and the correct mat is selected by what is the game that comes after the game that we're playing. And when we take all these parameters, we plug it to this equation, and we now compute the table winning chance, which is the probability of winning a table match. So we took all these algorithms, and we made a program available in the Android Play Store, and we evaluated our approach against the human opponents. From the period of 2020 to 2023, we let the agent play games against humans, and here are the results for all the games. We also played not only table, but Portes matches, Plakoto matches, individual matches, and the Ferga matches. And here we can see the evaluation of the humans and the agents. With the blue lines are the evaluations of the AI agent playing with one ply, and with the orange line is the evaluation with the two ply. And for the human opponents, we computed all these are the elos of the computed for the AIs. For the human opponents, we computed the elos of all human opponents, and we selected. We show here what is the best elo of the human opponents. The best elo of the human opponents is with the green dotted line, and with the other dotted lines are the average elo of the AI. So we see in all these match types, the AI clearly surpasses the human opponents, even the best human opponents. So a few words I also want to say about the system architecture of the project, and because we all have these algorithms, but it is important that these algorithms are executed efficiently in the hardware that we have available, the engineering aspect of the system. So in the Palamedes project, where there is the Palamedes core system, which is the principal component, and this component provides the following modules. We have the games where all the variants that are supported are inside. Mostly the rules of the game, how to play the game, how to produce all the available moves. And then we have the evaluators. We have a main type of evaluators, neural network evaluators, and other evaluators. Another module is the algorithms, the search algorithms, and all the inheritance that I have talked. There is also a few other accessory modules, such as the BG file modules that load save games, the training module that is used to train the games. This training is done offline. And also there are tests and benchmarks to verify and to compare all the approaches, not only for the strength of the AIs, but also for the computational effectiveness. So this is all the modules that are supported for the project up to now. These are the games supported are Backgammon, Portos Plakoto, Fevga, Nadre, Tavli, Hypergammon, Takhet, Nakgammon. We have a few evaluators, and these also the algorithms, Spectramax, Negabats, IDDFS, and of course all the other enhancements like CAS and filtering, and there are also a rollout module that will be available shortly. With BC5, we have 3 file formats that are supported. There are a few self-training, self-play training algorithms that are supported from the project. Some of these are experimental and are not available to the public, but will soon be available. Now I want to talk about the outputs of the project. We have 2 applications. One is a desktop application that is called Polygammon. With this application, the user can play the game against the AI and store and replay games, and also perform position analysis. This application is mostly for professionals and players that want to improve their game. There's also an Android application where we collected all the data that I showed earlier, the evaluation of against the human opponents, where the player can only play the game in his or her device against the AI. All these applications are freely available, and I have the links where you can download them. Also for the Backgammon application, you can search in the Play Store and download it in an Android device. Finally, of course, we have the papers and the research output, where I have all the papers available if you want to read them in the following GitHub repository. So I also want to talk about how Palamedes project what is the comparison between the other available programs that play effectively Backgammon and some variants. I have selected only that programs that are available to the general public. Extreme Gammon is a commercial application. GNU Backgammon is a freely available application, open source. BGBlitz is also a commercial application, and Logas is an application that plays mostly Narde. So the first 3 are only situated around Backgammon, and the last one is only situated around Narde. So Polygammon can play all these variants that the other programs cannot handle. And also for the AI edging, we see that some of the things that I've talked about, pruning, net, cuts, filters, this is also supported from the other programs, but some things are not, like search algorithm alternative. You cannot select which algorithm to play against. There is only one algorithm that is used inside their AI. And also the one thing that is not available in Polygammon is cube evaluations. This is not currently available. It will be available sometime in the future. So that's all for me. Thank you for your attention.
Thank you, Professor Dr. Papahristou, for the presentation. We can have several questions. Maybe I start one myself. So there are some, at least I know one variant of Backgammon, Hypergammon, that is considered solved. And it had 8 million positions. But for the normal Backgammon or other variants, I think the number of positions is too high. But is there any hope that maybe this AI can somehow get closer to make it solve, or you think it's still very far?
Yes, for Backgammon, the number of states of positions is 10 to the power of 18. The higher game that I am aware that has been solved is about 10 to the power of 14. So there is hope, but I think it will take a few more years. This, I mean, for fully solving the game, or when we call fully solved is when we know the outcome of all the states. So this is not a prerequisite to solve the game, because most of these states will not be seen in practice. So if we solve a sub portion of them, maybe we can call that we solve the game. So firstly, we have to solve a small percentage, which is the race part. There is the race condition where there is no hitting. And if we do that, then we can go to the next level and solve more states.
I may ask one more question, and then I let the audience ask some questions. So, for example, yesterday we had a speaker, Professor Rethio from GeoGebra, and he was giving different concept about difficulty of proving a geometric theorem. So one is the logical difficulty, that they count the number of steps that you need to do to prove that theorem and taking the minimum. And then there was also an algebraic difficulty, which was degree of a specific polynomial, which was the computation if you want to approach it algebraically. Is there any difficulty, like there are many variants of backgammon, and I saw that if I remember correctly, your thing can change the dices, they can change some other things to create new variants, right? Is there any concept of difficulty that we can compare these different games and give them some score of which one is more difficult than the other one?
Yes, there are some work in this area, but it's very difficult because there is also the chance factor, especially in backgammon games, where you can be the best player and lose the game because you have bad luck. So we have to take away the chance. Firstly, we have to see how much is chance affecting his game. So if chance, we have 3 or 4 games, chance is affected less in one game, then we can say that this game is more skillful, if you like. I don't know if this is answering the question. We want to know what game is more difficult than the other. That variant is more difficult to play.
Yeah, it would be difficult because of the chance, but there can be some mathematical kinds of definition we can put it. Maybe we can discuss it later. Is there anyone from the audience want to ask a question before we move to the next speaker? Maybe some quick question from the audience.
Sorry, may I ask a question?
Okay, Dr. Chatrapun.
Of course.
Yeah, thank you for interesting presentation. Sorry, I lost 5 to 6 minutes at the beginning of your presentation. Just I am asking this question for clarify the presentation and topic for myself. You said you have done an AI technique, but what we can see here, it is a recurrent algorithm plus a search algorithm. And if we get back to the train and test, some plots for train and test evaluation, I don't know how we can guarantee the convergence of this, for example, playing a game.
So how we guarantee, if I understand correctly, the conversion of the training algorithm?
Yeah.
Yes. We cannot guarantee it, but we can see it that with this approach, as far as I have seen, it works. The algorithm learns and learns quickly. Now, if we have a neural network with some capacity, how do you know that we have reached the maximum capacity of this neural network, that the knowledge that we put in this neural network is the maximum that we could? This is a difficult question. So the algorithm trains, converges. We don't see it decreasing. We don't see it. It just stays to the asymptotic and top that it can and stays there.
Yeah, thank you. Just a quick follow-up. If we go through the Banach space and using a fixed point theory, we might be able to prove the convergence of each game. And I think this is very important. Maybe I can share with you some references later and have a look.
Yes, of course.
Yeah, thank you.
Thank you very much.
Okay, let's thank Dr. Papahristou again for the great talk.